I recently converted my Vento Triton with a Chinese Minarelli horizontal two-stroke engine from air-cooled to liquid-cooled. This video won't be a strict step-by-step how-to, but I will go over a lot of info related to the process and share my experiences so you can see what's involved in detail. Hopefully at least some of it is useful for anyone considering a liquid-cooled swap on a scooter and not just for the Minarelli and clones. Let's start out with some pros and cons of liquid cooling versus air cooling. The most obvious negative is the increased complexity of the cooling system using liquid instead of air. The most common modern air-cooled scooters use a forced air cooling system. The crankshaft drives a fan that moves air. Shrouds around the engine channel that air across the cylinder and head to cool them. There are air-cooled engines that rely solely on airflow from the movement of the vehicle, but most scooters use forced air cooling. Not a lot of parts are involved in an air cooling system. On the other hand, a liquid-cooled system can have quite a few parts. The bare essentials being a radiator or radiators, hoses, a water pump, and coolant. Some systems may also include a fan or fans, various electrical components like switches, relays, and wiring, an overflow or expansion tank, and a thermostat. In a liquid-cooled system, the engine has coolant passages for water or other coolant to move around it. Heat from the engine is transferred into the coolant, which then travels to the radiator. Coolant passes through tubes in the radiator, where air around the tubes cools them and the liquid within. This is particularly effective when air is moving, like when the vehicle is in motion or a fan is used. The cooled liquid then gets pumped back into the engine by the water pump, and the whole cycle repeats. Now that you know the basics of each system, it's not difficult to see that the liquid cooling system is a bit more complicated. That complication extends to maintenance and modification. With an air-cooled engine, as long as the cooling shrouds are free of debris and everything is secure and intact, it should work as intended with essentially no maintenance. Liquid-cooled engines can suffer from leaks, air pockets trapped in the system, corrosion, freezing in cold weather if antifreeze is not used or up to par, and there are more parts to fail. If you want to service engine internals, you don't have to remove shrouds in most cases, but you will usually need to drain the coolant and then refill it afterward and make sure all air is bled out. If you want to change engine specs, like squish clearance for example, that's the distance between the piston crown and the cylinder head, it may be more complicated than what you're used to with an air-cooled engine. That's because you have more sealing surfaces to deal with on liquid-cooled parts, and using O-rings on many setups means that you can't modify any surface you choose very much without considering O-ring fit or alternative sealing methods. You certainly can modify them, but it tends to be a different process with more considerations. The rest of the cons that I'll mention are basically a function of the more involved system. The parts of a liquid-cooled system and the liquid coolant all weigh something. I'd guess on average you're looking at 5 to 10 pounds heavier, which probably makes no practical difference on anything but the most competitive racing builds. Cost goes hand in hand with the amount of parts used. More parts generally cost more money. Plus, liquid-cooled cylinder kits are usually a little more expensive, and sometimes a lot more expensive than comparable air-cooled cylinders. So now the question is, with all of these negatives, why would anyone want to switch to liquid cooling? Let's look at the pros to find out. I'll start the pros with lower temperatures. A good liquid-cooled setup can see operating temperatures significantly lower than the average air-cooled rig. Air-cooled engines often rely heavily on excess fueling to keep temperatures in check, but the additional fuel is not so crucial when liquid cooling is employed. Being able to use leaner mixtures can have the added perks of slightly more power, better fuel economy, and lower emissions. Liquid cooling is also more consistent. The temperature of a liquid-cooled scooter tends to stay in a more narrow range than air-cooled engines. The less parts fluctuate in temperature, the less they fluctuate in size from thermal expansion and contraction. That can allow tighter tolerances for engine components and aid in reducing wear and increasing longevity. Consistency, combined with the aforementioned lower temps, can also increase reliability and power on longer rides due to less heat soak. This can be very noticeable in two-stroke engines because the air-fuel mixture passes through the crankcase and cylinder before entering the combustion chamber and soaks up heat, becoming less dense. Another plus of liquid cooling is that you may lose less power by not having to drive a cooling fan with a crankshaft like a forced air-cooled engine. Driving a cooling fan is estimated to use up as much as 1 to 2 horsepower in these small engines. Crank-driven water pumps will still cost you some power, but not nearly as much as a fan compared to an appropriate pump. Electric water pumps burden the electrical system instead of directly putting drag on the engine. Another advantage is the availability of high-end racing parts. If you have a 2-stroke, and possibly even some 4-stroke applications, you'll find that the top of the line, baddest combos available are only sold in liquid-cooled versions. Racing engines are very demanding and can generate a lot of heat, and liquid cooling deals with that better. The last pro that I'll mention is that liquid-cooled engines can be a little quieter because the liquid around the engine components can dampen sound. This is a pretty minor pro to me, since most modified scooters tend to have louder exhaust anyway, and noises carry through the rest of the engine that isn't surrounded with water. The majority of the pros and cons can be simplified for a mostly accurate, easy summary. Liquid cooling does a better job of keeping the engine cool consistently, with the primary drawbacks being complexity and expense. My scooter is a modified 2-stroke that I usually big bore and stroke to 96 or 103 cc, and I take it on long rides that often last 6 to 12 hours somewhat regularly, so I thought it was finally time to see how liquid cooling worked out for it. I hadn't given the scooter any attention much beyond engine or CVT work for years, so I wanted to take it down to the frame anyway and make some other changes, so now was as good a time as any to do the conversion. The part that seemed the most difficult to me was trying to figure out what radiator or radiators I wanted to use and how they would fit on the scooter. There are lots of radiators available for scooters, ATVs, dirt bikes, and motorcycles that could make excellent choices. Smaller radiators, like this stock unit on a Derby Predator, are easy to install and hide, but won't have as much cooling capacity as may be desired or required. Large radiators may be able to keep the engine cooler, but they're harder to install and tough to conceal. You can research engines similar to yours to get an idea of the size that you'll need, but many people doing water-cooled conversions choose to go big with the radiators. That's the way I went. I chose a pair of radiators from a 2005 to 2013 Yamaha YZ125 made by GPI Racing for under $80 on eBay. They were intended for a 2-stroke bike with a larger engine and about double the power that I'd expect to use them with at any point, so I thought they should be overkill, but overkill in a good way. I had no plans of using a cooling fan, and didn't care about hiding them, so I knew I wanted more radiator for insurance on longer stops. 2-stroke riders also tend to try to run the coolant at very low temperatures compared to what many of us may be used to for cars and motorcycles. From what I read and what was discussed on the forum, as low as 120 degrees Fahrenheit could be desired by some riders. This is because the air-fuel mixture travels through the crankcase and then up through the transfer ports into the cylinder. Keeping the intake charge cooler keeps it more dense and reduces power loss from heat soak. In addition to the sensible arguments for larger radiators, some like their appearance. There are quite a few options if you would like to use dual radiators. I thought the connections on these were in better locations than some similar radiators from other bikes. Probably the best large dual radiator setup that I've seen for appearance comes from scootertuning.ca. They use radiators with the inlet and outlet both on the bottom, and that makes routing hoses a little bit easier to do neatly. They also come with a bracket designed as a bolt-on for 2002 to 2011 Yamaha Zumas that makes them easier to install. The big drawback with those is the cost being around 3 times what I paid for the YZ125 radiators, but I did have to put in a lot more effort to make mine fit and look decent. I started out by trying to figure out basically where the radiators would be on my frame. You may notice that I have cardboard covering the cores of the radiator. That's a simple way to protect the fins from damage while you work with them. My front foot pegs were either going to be in the way or at least not usable, so I had to cut those off and then grind them down. I didn't like the extra mounts on the YZ125 radiators, so I carefully removed them with a cutoff wheel and then ground, sanded, and lightly polished the areas to finish. Then I made up a bracket out of 1/8 inch thick by 1 and 1.5 inch wide steel flat bar to mount to the frame. M6 by 1.0 bolts on the sides would let me slide the radiators over and secure them with a nut using a set of mount bushings from a YZ125 that the radiators were intended for. Unfortunately, the radiators could move more than I wanted with the bushings in place. On the YZ125, they would have used the other brackets that I cut off of them and additional mounting points to keep them in place better. I ended up making a set of aluminum spacers and washers on the lathe to fit the mounts and keep them more rigid. The leg shield had to be cut down so it fit around the radiators and left room to remove the radiator cap. Rough cutting was done with a cutoff wheel, and then adjustments were made with a sanding wheel until it eventually fit, and later the edges were sanded with sandpaper. In my case, the radiators are very open to airflow all around them, but if your setup is more hidden, you will need to make sure they get plenty of air from the front when the scooter is moving, and also have room behind them. Without ample space behind the radiators, air can't pass through well enough for proper cooling, so be sure to make cutouts behind your radiator, or at least try to leave a few inches of free space behind them. If a radiator is mounted where it's not as open to airflow from the front as you'd like, you can try to shroud the area around it to encourage air to move through the radiator core. There is no one right way to mount a radiator, so with some creative thinking and research, there are lots of possibilities. Before moving away from the radiator talk, I wanted to show you a few pics from members of the 49ccscoot.com forums. These pictures show a front mount rig that is set up in a way that it could be removed without a trace if needed. Here you can see the small radiator used on the Honda Metro and Ruckus that mounts in front of a crank-driven cooling fan. The fan is similar to what air-cooled engines use, but in this case it moves air through the radiator, and that means that the radiator is getting airflow even when the scooter isn't moving. Similar designs can be found on other scooters like the Yamaha C3 and S-Max. The water pump was my next consideration. Some stock scooters with horizontal Minarelli 2-strokes are liquid-cooled with a mechanical water pump that sits where the fan and shroud normally would be and are driven by the crankshaft. A few examples would be the Yamaha Aerox, Malaguti F12, and some Aprilia SR50s. Pumps from those could be used, or there are aftermarket versions from a few companies. There are also more universal mechanical water pumps that use a pulley on the pump and a pulley on the crank to be belt-driven. Some use more traditional cogged drive belts, and others use an O-ring as a belt, but O-ring driven units may be more prone to slipping, especially in wet conditions. These may require custom brackets for the water pump mount and a custom or modified pulley to fit the crankshaft. Possibly the most popular for conversions are electric water pumps. There are quite a few pumps sold by aftermarket scooter parts companies, as well as options from automobiles or other sources. Electric pumps don't cause a direct loss in horsepower because they are driven by the battery instead of the crank, but electrical load on the charging system may still cause some loss. I think the load or loss that suitable electric or mechanical pumps create should both be almost inconsequential, likely speaking about a small fraction of a horsepower. You will need to have a charging system capable of supporting the load of the pump for real street use. Relying solely on battery power with no charging will create zero loss in horsepower, but ride time will be limited based on battery capacity. Pumps used for scooters commonly range from about 0.4 to over 1.5 amps of continuous draw, which is roughly 5 to 20 watts. If your electrical system is already stressed from lights or other accessories, you'll need to consider a mechanical pump, reducing other loads, or finding a way to increase charging output to use an electric pump. Here's an example of a common way to wire an electric pump to come on whenever the key is on. Some prefer manual switching, but this way you can't forget to turn the pump on or off. I decided to use a stock-style bolt-on mechanical water pump, so I wouldn't have to worry about the electrical load, and I assume they are pretty tried and true option since quality scooter manufacturers have used them for years. The only negative for me was that I heard a few reports of pumps leaking or seeping even after changing seals, but it didn't sound like a major problem. I went with a pump made by Hoka that included the housing, pump, and drive wheel. The pump has to be driven by the crank, so I also needed special studs that screw into the flywheel, as well as rubber bushings that fit on them. The studs and bushings made up with holes in the water pump's drive wheel to drive the pump. For that reason, some racing ignitions may not be compatible with these pumps. Installing the pump was simple enough. I screwed the studs into the flywheel and tightened them, then pushed the rubber bushings over the studs so they sat in the groove in each stud. Then I tried to rotate the flywheel and the drive wheel on the pump so that the studs aligned with the holes in the drive wheel, and installed the pump by tightening both bolts evenly. You may want to put a very thin film of grease on the rubber parts to help them slide into the holes on the drive wheel, and it's a good idea to make sure that turning the crank also turns the water pump. The mechanical pump has 3 bolt holes, but my cases only have 2 threaded holes. Some cases can use all 3 bolts, but I haven't had any problem with using 2. Once the cylinder and pump were installed, it was clear that I'd need to do something to cover the hole in front of the stator and flywheel. Some leave the space open, but others like to use a cover as a little protection from debris and water, though covers aren't usually totally sealed. You can buy stock covers from something like a Yamaha Aerox or Apex or DRR ATV that had the liquid-cooled Minarelli engine, or you could make your own. I chose to make my own from 1/32 of an inch thick aluminum plate, but I started by getting the design worked out using some flashing that I had around. The flashing is thin and easy to cut and work with to make a template, but some people use cardboard or poster board. Others go straight to working with metal that they want for the final product if they're confident in their metal fabrication skills. I came up with something that would work with flashing, and then transferred that onto an old yard sale sign with a couple of revisions to the shape that left extra room for sanding or grinding for a tight fit. Then I used that to mark and cut the aluminum. I did some fine-tuning and then copied what I had onto the old sign again. This way I could keep the layout as a template and share it for anyone interested in saving a little time making their own. Check the description of this video for a link to the template. The water pump cover has M5 by 0.8 threaded holes for the stator cover to attach to, so I drilled holes for those. Then I was worried that the plate could vibrate and make noise without support on its other side. All of my 2-stroke builds are premixed, so I had threaded holes in the cases where the oil injection pump would normally mount to help me add support. I cut a spacer in the lathe, and then used a long M5 bolt to secure the bottom corner. Then I drilled and tapped the case where the upper corner of the plate would sit, but only after making sure it was safe to drill there. That let me put a 4th bolt in the cover so it's secure on all 4 corners. I'm not sure that it was necessary, but it can't hurt. A little polishing finished it off. I guess I'm going backwards a little here, but I thought I should mention the cylinder kit. I used a Motoritech 54mm big bore kit, but most kits intended for this application should be a pretty similar setup regarding liquid cooling. The cylinder itself should have an inlet for coolant and the head should have an outlet. You may notice a spot for a thermostat to mount on the underside of the head in the outlet. Thermostats are used to try to regulate coolant temperature by controlling coolant flow through the system. The thermostat blocks most flow from the engine to the radiator until the coolant around it heats up enough for it to open and allow coolant to circulate. This can be useful for warming up an engine faster or maintaining a desired operating temperature, as long as the rest of your cooling system is capable of running as cool as the thermostat's rated temperature. I didn't use a thermostat because I wanted the system to operate as cool as it could. You may also have a spot for a bleeder valve at the top of the cylinder head, which can help eliminate air pockets in the system. I bought my bleeder valve as a stock replacement part for a DRR or Apex ATV, and you should be able to source them from a water-cooled Minarelli powered scooter. They are also typically the same M8 by 1.25 thread that's common for brake bleeders, so that may be an option if all else fails. When it's time to assemble the engine, the base sealing should be no different than air-cooled cylinders, but the head will be a little different. Most use two O-ring style head gaskets, one around the bore and the studs, and another around the outer edge of the cylinder head. A few use a metal gasket around the bore and studs instead. I lightly coated my O-rings with Permatex Ultra Gray RTV, but there are plenty of alternatives. I also put a thin layer of RTV all around the deck of the cylinder. Be sparing with sealant. You don't want globs of it to push out when tightened. A little goes a long way. Follow the assembly and curing guidelines from the sealant's manufacturer. Many heads have a threaded hole that can be used for a coolant temperature sensor or sending unit. I believe 1/8" NPT is the most common thread, but it may vary. Whether you plug the hole or use a sending unit or sensor, I would suggest using a thread sealant. I used a nylon washer from a hardware store under my temp sending unit, and then coated the threads with high temperature thread sealer made by Permatex. You could use Teflon tape instead. That brings me to coolant temperature monitoring. As shown, one easy way to keep an eye on coolant temp is by using a gauge with a sending unit that fits in the cylinder head. There are also fittings that can go in line with coolant hoses to make adding a gauge simple. Brands like TrailTech, Coso, Stage 6, Autometer, and many more offer coolant temp gauges, so it should be easy to find something you like. I used a TrailTech TTO temperature gauge with a homemade mount that screws into the switch assembly right where the stock mirrors used to be. With most components installed, it's time to connect everything with hoses. 5/8" or 16mm inside diameter hoses worked well for the majority of my connections, but measuring your inlets and outlets will tell you what you need. Clear reinforced coolant hoses are popular with scooter tuners, but I chose to go with plain black automotive heater hoses because they were rated for higher temperatures and have always been durable for me in cars and trucks. Silicone hoses are another option, but they tend to be kind of pricey. You'll also need hose clamps. It's not necessary with all types of hoses, but I like to use liner clamps that feature a smooth liner so they don't cut into your hoses. Whenever you tighten hose clamps, they shouldn't be installed as tight as you can get them. You just need them to be snug and secure. Hoses must be routed a certain way to allow your cooling system to work at its maximum potential. Coolant should be moved from the radiator's outlet, through the water pump, into the inlet on the cylinder, out of the cylinder head, and then back into the radiator. When a radiator has top and bottom connections, hot liquid from the head goes into the top connection, and cooled liquid exits at the bottom connection toward the water pump and cylinder. An easy way to remember this is that heat rises, so the hot inlet side of the radiator is the top side. It's also important to make sure water is flowing the right way through your pump. For the stock-type Minarelli pump, the lower connection is the inlet, and the upper is the outlet. You can often look at pumps and tell which is the inlet by their design. The most common style's inlet sits outward the most on the pump. Some may have arrows or other markings, and it's never a bad idea to check for information from the pump's manufacturer. Standard coolant hoses tend to crimp if bent at too sharp of an angle, but you can buy preformed hoses, hoses with internal springs, and even external add-on springs to keep hoses from collapsing. You could also use things like 90-degree plumbing fittings to deal with tight turns. Most radiators also have a port just under the cap for overflow or expansion. This is sealed off by the radiator cap under normal operation, but if pressure in the radiator overcomes the spring pressure of the cap, which is usually 16 psi or about 1.1 bar, the port is exposed and coolant and/or vapor can flow out. When the system cools, a vacuum may be created in the radiator, and a valve opens and allows air or coolant to get back into the system. If an overflow tank is used, hot coolant can flow into it and then be drawn back in when the engine cools. Some just attach a hose and route it so if any coolant or steam comes out, it won't be a hazard to the rider or get on the brakes, tires, or other critical parts. I was told by others that had done liquid-cooled conversions that they had no trouble with just a hose on the overflow port, so I just ran a hose toward the ground and secured it. With the cooling system in place and plumbed, there wasn't much left to do but add coolant. There's a seemingly endless supply of options for engine coolant, so which should we use? Water actually does fine keeping the engine cool between its freezing and boiling temperatures, but antifreeze or coolant can extend its operating range by lowering the freezing point and raising the boiling point. In addition, coolant contains rust inhibitors that protect the things in contact with coolant from corrosion. Ethylene glycol and propylene glycol coolant should be compatible with most scooters. Ethylene glycol is the most popular and typically lower cost choice. Propylene glycol is non-toxic, or at least less toxic, so it may be a better choice if pets or animals could be around spilled or leaked coolant. Antifreeze typically needs to be mixed with water, unless you buy pre-mixed or ready-to-use coolant. Always check the label to find out if your coolant needs to have water added. If you do have to add water, distilled or deionized water is preferred over tap water, because tap water can contain minerals that lead to scale and deposits in the cooling system, which can eventually cause clogs and poor cooling. I used Bel-Ray Moto Chill in my scooter, mostly because I already had it around from my T-Max, and it's a propylene glycol coolant. Before filling the system, I loosened the bleeder valve on the head. Then I began pouring coolant in through the filler cap on the radiator while watching the bleeder screw. I closed the bleeder once I saw coolant coming out of it, then continued to fill the system until coolant reached the top of the radiator, just below the neck. The system then needs to be bled or burped to get rid of air pockets that may be trapped. In my case, the radiator filler neck is the highest point, so I just left the radiator cap off and started the engine so coolant would circulate and air could rise to the top to be bled out. In systems where the filler neck is not the highest point, you may be able to elevate part of the scooter to make the filler the highest point. Having no thermostat, my system bled out a small amount of trapped air quickly, and I kept it topped off with coolant. I let it heat up anyway, just to be sure everything was working properly. In a system with a thermostat, you need to let the engine warm up so the thermostat can open to allow the coolant to circulate and bleed the air out. Once the coolant level is no longer dropping and you aren't seeing any bubbles, the system should be free of air and the radiator cap can be installed. I ended up using just a little over a liter of pre-mixed coolant after filling and bleeding. It's a good idea to look for coolant leaks while the engine is running and after it has sat for a while. Also watch for steam from the exhaust or in a 4-stroke any mixing of oil and coolant, which would indicate sealing issues that need to be attended to before moving on. Now the cooling system should be ready to go, but remember to keep it maintained. Check coolant level periodically when the engine is cold and top off as needed. If you lose much coolant regularly, you'll need to figure out why. At this point my build needed some buttoning up and lots of tuning, but it was mostly together. I haven't told you a whole lot about what the setup is, so here's some info to get you up to speed on what I'm riding before moving on. The reason I noted some swaps in the list is that I spent way too much time trying to get a 24mm carburetor and larger intake and reeds in tune for a good throttle response. I tried pretty much everything I could before switching to a smaller carburetor and related parts, but it was a waste of effort. As soon as the 21mm carb was installed, it was a totally different machine on quick throttle.